So here you have the pre-mRNA, and the 5-cap provides stability to it, and also in it has 2 exons and the intron. So the snRNPs contain protein and snRNA. The snRNA binds at the intron-exon junction, and then other proteins also join in to create a spliceosome. The snRNPs act as ribozymes, which cleave the intron out of the pre-mRNA, and it is degraded. And then also the spliceosome components is also released. And then the remaining 2 exons are cleaved together by the other proteins. And the 5-cap it continues to add stability, and also in the addition of a poly A tail, it adds additional stability.
Go.
In this situation, tryptophan is absent, the repressor is inactive, and the operon is on. So here you have the regulatory gene, TRPR, and this codes for an mRNA, which codes for an inactive repressor. And since it's inactive, it doesn't bind to the operon, so the RNA polymerase, which binds to the DNA at the operon promoter, it's free to move down the chain and transcribe the genes of operon. And so then this transcribes mRNA, which codes for the polypeptide subunits that come together to form these enzymes that allow for tryptophan synthesis and creates tryptophan. So in this situation, tryptophan has accumulated, and so to inhibit the production, the synthesis of more tryptophan, the tryptophan binds to the repressor, and then this causes it to change shape and become an active repressor. And the active repressor binds to the operator, which derails the mRNA and inhibits the RNA polymerase, and so no RNA is made. In the first situation, lactose is not present. So here you have the lac operon, and the regulatory gene LAC1 transcribes mRNA, which codes for an active repressor. The active repressor binds to the operator, which hinders the RNA polymerase. In the second situation, lactose is present in the form of allolactose, which binds to the active repressor, and this causes it to change shape and become an inactive repressor. Since it's inactive, it does not bind to the operator, which allows the RNA polymerase to transcribe the LAC-Z, LAC-Y, and LAC-A. And these genes code for beta-lactosidase, permease, and transacetylase. And so beta-lactosidase, it hydrolyzes lactose to glucose to galactose, and permease allows lactose to enter the cell, and transacetase has no known function. So lactose is present, so then allolactose binds to the repressor, which makes it an inactive repressor. So then, so lactose is present, and when glucose is scarce, you have high levels of CAMP. So the CAMP will bind to the inactive CAP, and then this causes the inactive CAP to change shape and become active CAP, and this binds to the CAP binding site at the promoter of the DNA. And then because it's shaped like this, the RNA polymerase can bind to the active CAP, and then the RNA polymerase can move down the chain and transcribe and it'll synthesize RNA. Okay. And then in the next situation, when lactose is present but glucose is abundant, you have very low levels of CAMP. So it's less likely that the CAMP will bind to the inactive CAP. So the inactive CAP will stay as it will stay inactive, and then so then it will be very unlikely that the RNA polymerase will be able to move down the chain and create RNA. Activators bind to the distal control element, which is grouped on the enhancer in the DNA sequence. And then the DNA bending protein causes the DNA to bend so that the activators are moved closer to the promoter. And then nearby you have the mediator proteins and the general transcription factors. So the mediator binds to the mediator proteins bind to the activators, which binds to the general transcriptional factors, and also binds to the RNA polymerase 2. And then this assembles the active transcription initiation complex. And this increases RNA synthesis and creates more mRNA.